Okay, so the purpose of this video is to give you sort of a top-level look at all the equipment required to do this continuous wave NMR. So let's just, I guess, start over here. What you have over here in these big white boxes are coils wrapped around iron, which is an electromagnet. So you can barely see, or you can see here the red and black leads going into these coils here. This comes from this power supply over here, which is used to supply current to the electromagnet. And it's sort of in a transformer configuration where, if you look very carefully, the magnetic fields can be created at the metal core inside these coils here. And of course, it's sort of transmitted around a bit, so to speak, in these big chunks of metal that are at 90 degrees relative to that, because we need the magnetic field to exist in this gap right here where you see sort of this brass fitting in there. So that's sort of what this big first part is over here. It's a big electromagnet, and it's possible to get some fields up around about 8,000 Gauss or so with this electromagnet. Okay, that's the first part. The next part, that as long as we're talking about the magnet here, inside of this brass holder right here that you see is where we put our sample. So I'll zoom in a bit on that right here. You can see the sample is sort of placed in a hole in the magnet, and this is the water with a copper sulfate in it. You can barely see it. It's kind of this bluish water here that we're talking about. And there's a hole at the very top. You just sort of drop it in like that. And if a strong magnetic field is going to be created by these coils, then this sample is going to be immersed in that magnetic field. And that serves for the primary static magnetic field that all the protons in the water are going to precess around according to the NMR theory for getting it set up. So that's sort of what this big first element is right here. Big electromagnetic sample holder to immerse the sample in our magnetic field. Then we go over here, the center box right here is sort of the control box for the entire experiment here. The first thing we see here is the NMR oscillator, as it's labeled right here. And it always gives you the frequency that the RF is being applied at in megahertz. Now, where does that get applied? Well, if you go back to the sample holder, you can't quite see it even if you're in person, but this sample here, as I drop it into this hole, is actually in a coil. So the coil of wire is immersed in this magnetic field, and that coil that this sits in sort of behaves like a solenoid, if you will, and so this sample is in a solenoidal coil. This RF at the moment here of like 16.9977 megahertz, that's what's being applied to the coil that the sample sits in. Okay, so that's sort of what that does. That's the RF, or radio frequency, as a long name. And then if the coil picks up this absorption of photons, it'll sort of come out of this line here to the NMR signal that heads to an oscilloscope. And of course, if I have a frequency right here, which is this big sine wave, then it seems like it would make sense that I can control both the amplitude and the frequency of that sine wave, and indeed I can. So you can see if I just put my hand on this and start turning it down, see the frequency goes down. If I turn it up, the frequency can go up. So we can change the frequency of the RF that's applied to the sample there. And of course, I can change the amplitude as well. And the box is kind of has some strange behavior, like if the amplitude is too low, it just goes to zero frequency, and I either have to see, I'm just turning the frequency knob and nothing's happening. Nothing seems to happen. It sort of kicks in again there, so nothing was happening, suddenly it kicks in again. So we try to avoid situations like that, but it's not so hard to do. But in either case, there's the amplitude and frequency, and I'm sure that has something to do with the electronics required to pull off a megahertz oscillator like that. Okay. The next part over here, the second half that you see, has to do with that magnetic field modulation. And so if you look back to the original setup over here, remember here's the coil which sits in a solenoidal magnetic field, and then inside that strong DC magnetic field supplied by the coils here, there's these small gray coils that sort of exist around the magnetic poles there. So these are like little solenoids themselves that can produce a magnetic field kind of this way too, if current is piped into them along these wires right here. So see, there's some other coils here. This is a so-called wiggler magnetic field, or the modulated magnetic field. So you can imagine having a static magnetic field provided by the electromagnet here. Then on top of it, you have these little coils, and the magnetic fields can sort of superimpose in the region where the sample is. So it's all sort of, say, along this x-axis here. So the magnetic fields can superimpose. So what these allow you to do is add a little bit of a modulated magnetic field on top of the otherwise static magnetic field that comes from the electromagnet. You can read all about in the lab manual why we need that. So in either case, the couple controls for that the magnetic field modulation are the time that it goes up and down, sweeps back and forth, either fast or slow. fast seems to suit us best for this experiment. We can change the phase of it too. In other words, when the modulation sort of begins to rise and fall, just like a sine omega t plus a phase, you sort of know what that does. And of course I can control the amplitude of the modulation as well, which really isn't a critical parameter for this experiment, but obviously if the modulation was really, really small, it would be hard to find the NMR resonance, and if the amplitude was larger, it just makes it a little easier to sweep past it. So what am I talking about? Say the NMR resonance is right where my finger is here. A very small modulation magnetic field might sort of have us modulate past it like this, but a very large one would have larger swings like that. And obviously if you don't know where this resonance is here, it's nice to have a larger sweep field, so at some point you can hit it and get that response on the oscilloscope. Like if you're modulating really small like this and the resonance is over here, you'd never see it, so it's nice to sweep past. So it turns out that we're not that sensitive in this experiment, and the amplitude, once we just sort of set it to something, seems to carry us through the experiment okay. And here are the two wires that leave the modulation here, these two white cables here that sort of feed these two white wires on those small flat solenoids that sit around the magnetic field coil. A pretty standard setup for nuclear magnetic resonance, or NMR here. And that's about it. The only thing that we last to discover over here to have is this is a power supply that supplies the current to the electromagnet. It's sort of a good strong power supply that can do about 10 amps. We usually never need to go above about 3 or 3.5 amps with this experiment. And of course I have a trusty ammeter wired in series with the wire leading to the magnet here, so we always know exactly how much current is going to the magnet. And that's about it. And then the last part that you see then is the oscilloscope here. And what the oscilloscope has on it is I will pick up on in the next video.